Congratulations with finishing your first design in eDesign. I know it was daunting for some of you, but hopefully you've learned something. So I thought it would be a good idea to just talk you through some of the aspects that I saw some of you struggling with. So I've designed this circuit for a specific input, namely 10 millivolts per division or per degree C and 500 millivolts at 0 degrees. So I'll talk you through the signal first. So this is the signal that I've set up. If you apply that there, then you will find 34 degrees correspond to 840 millivolts. And then the next degree up from there is 35 degrees, will be at 850, and the next one will be at 850. Then 34 degrees again, and then I've stepped it up to the max of 42 degrees. So the reason I've done this is I wanted to check and confirm the step response, so the time that it takes for the output to reach 90% of the full output for 1 degree step. And then I've stepped it back just for good measure, and then made a massive leap just to see what it looks like. In the config file, just so we're all on the same page again, in the config file, this was the noise. I've put in a noise of 50 Hertz and 1 degree Celsius plus and 1 degree Celsius minus on the AC. So the amplitude of my AC is 1 degree Celsius. Many of you thought that this was the signal in some way, but it's obviously not. So let's just go to this circuit and how it, just talk through how it works. So I'll start here because this is the heart of it. At the heart of my circuit is an operational amplifier which takes a difference between a filtered signal, a filtered version of the temperature sensor, compares it to some kind of an offset using a virtual ground, which is then transferred to V out. If you look at one of the last lectures I uploaded, if you use a differential setup like this one, the virtual ground, that 2.5 volts or whatever you choose, presents here as a DC offset. So I use my virtual ground to generate 2.5, and the reason I want to generate 2.5 is I want to reach the maximum that I can on the output, going to the positive of some middle point and to the negative of some middle point. So this middle point of mine, in this case, will be 880, because in the middle I have 38 degrees. So 38 degrees times 10 plus 500 milliamps gives me 880. So my signal, the middle point of the range that I want to measure, is 880. So I would probably want this thing here to be 2.5 volts, and this here I'm expecting to revolve or to go around 880 millivolts. So in some way I need to then adjust what goes into the amplifier to make this thing go around 2.5 volts to somewhere around 4, somewhere around 0. Anyway, so maybe let's talk about the DC offset first. So this DC offset here, if I don't take out the DC offset, that's the 880 volts DC offset on my input. If I don't take it away, then it will result in a big amplification of that DC voltage, which would blow the output right into the rail voltages as far as it could go. This is why I need to remove that offset, because this amplifies difference, and if you have a 0 here, then it's going to amplify whatever that DC voltage is and whatever the AC voltage is. And with AC, I mean variation around the middle point. I don't actually mean AC, I mean deviation from the middle point. It's not just going to amplify that, it's also going to amplify the DC. So I need to generate something to take away that DC, and you can see it's a subtract effect. You will recall the mathematical expression of this is V out is equal to VG plus the gain, and the gain is multiplied by the mathematical or the voltage difference of those two. I chose a gain of 47, And the reason I did that is because my signal is, let's just look at this real quick. So my signal will go from 880 to 920, and the difference there is 40 millivolts. So I want that to, it's 1.5 volts that I want to go up. So to do that, I need a gain of 37, more or less. So this is obviously millivolts, so you need to multiply that by 1,000, so 38. So I chose, in this case, I chose 47 to blow it up nice and big so that I get a big output that's as broad, that captures as much of the range that I possibly can. So let's just look at what I have here. I have the 9 volts generating a 5 volts through the LM7805. Then I have a few things. So I generate this virtual ground. I generate using a voltage dividing circuit. I use 500K. Many of you used silly low resistors here, which is just going to use unnecessary current. I used 500K resistors so that the current is really low, and the middle point of that is 2.5. Then I added a voltage follower, or a unity gain, or a buffer. The reason I use that buffer is because I don't want these voltages to be affected by this signal here, because that VG, virtual ground, is connected here. So if this thing swings around and goes crazy, it's going to affect my virtual ground. So obviously, if you want to measure relative to a virtual ground, you don't want anything to affect that virtual ground, because you need it to be stable to accurately measure relative to it. So this buffer gives you that.
E-Design 344 Lecture 5. Okay, so hello everyone. Under props request, I'm explaining why we're using buffers in our circuits. And basically it's to separate our circuits into different blocks so that we can basically use the op-amp as a way for the outputs to see a very low impedance. So it almost makes the outputs see like a positive voltage source, and then on the input it sees like an infinite impedance. So what that means is it probably draws very little current, and it doesn't have an effect on the circuit. So for example, if you had an op-amp buffer over here where my mouse is hovering, then that would mean that the output would almost see like a perfect voltage source, and then the input would see an infinite resistance over here. But in this case, I don't think it matters much because I don't have any other resistors loading the circuits. But if you had to have other resistors loading the circuit over here, then these resistors would have an influence, and then the current draw would be different. So basically, we're using the op-amp buffers in order to create like different blocks in our circuits, so that, for example, from this side, looking in here, we will see infinite impedance. Very low impedance. And then looking in from this side, we'll see infinite impedance, so that this side of the circuit does not load this side. Thank you.
Yep. So just for clarity's sake again, the reason you don't have an op-amp between R5 and, where you don't have a buffer between R5 and your U1 op-amp is because the op-amp does not have a current flowing into it. Its impedance is already infinite. If there were resistors,
if I, let's say, I had resistors over here, then these resistors and those resistors would obviously, they would mess with each other. Like there would be some differences. So I would have to add a buffer here. So that's
exactly. Yeah, and if you didn't have the op-amp at the top there, it would have affected the filter performance. R1 would have affected R9 and C3, and then also the gain would have been affected. The R1, R2 gain would have been affected by R9 and C3.
Right, the same goes for T offset. So in T offset's case, I need this thing to take away the DC that's present on the filtered signal. So this filtered signal of mine, I told you, is in the middle, or at least in the middle of that range is 880 millivolts, and I want to amplify whatever is away from 880 millivolts. So to take away the 880 so that I can amplify the difference, I used a neat trick here. I used a voltage divider, and I have had them add up to 500K. The reason I have that is I can quickly and easily see this is giving me 8 880 millivolts out of the 5 volts. So again, I use the voltage follower, unity gain, so that I can protect the voltage levels here. For if I did not have this unity gain here, these voltages will be affected by this one, but that'll be steady. And then because this V out may vary, it'll feed back and affect this voltage here. So I'm protecting both sides essentially. I'm protecting it against one another using this buffer. So it's compartmentalizing my design essentially. Nice and protected. Okay, so this offset I chose to be at 880 millivolts. So whatever goes on around 880, the 880 will be removed and the difference will be amplified. And that's what I want to do. So if it's perfectly 880 millivolts input, which will be 38 degrees, I want this to be 2.5 volts. If the input is 920, which will be 42 degrees, I want this to be maximum at 4 volts. So the 920, what will be subtracted is the 880 multiplied by a gain of 47, and that output will then be close to 4 volts. The same if it's at the bottom range, 840 millivolts, subtract the 880, I get 40 millivolts. That's gained or amplified by 47 gain, and that gives me something close to 0 then on this side here. Okay, so let's just look at the filter then. The filter that I have, I've just used a simple RC filter, so first order RC filter, and it is also connected to a unity gain or a voltage follower or a buffer. The reason I had to do this is exactly the same. I don't want this signal here to affect my virtual ground, and I also don't want the virtual ground in any way. If there's any changes there or any resistances there, I don't want it to affect this, or at least the stimulus signal. So I use this RC filter. I chose the RC filter cutoff frequency to be equal to 2.38 hertz. So that's quite low. And what you had to do now is to ensure that the signal from the 50 hertz noise, that 50 hertz noise is reduced substantially so that the output level is less than or equal to 80 millivolts. That's the one part of it. However, the competing part of it is that your rise time must be quick. So you can think of this as from two perspectives. In the frequency domain, it's a filter with a cutoff frequency, and it has a response. It has a frequency response. And that frequency response tells you what the amplitude is of a certain frequency. So 50 hertz will have a specific frequency response or an amplitude if it goes through this filter. So that's the one part of it. So you had to do that. But there's a competing requirement. The competing requirement is in the time domain. And this seems to have thrown many of you. In the time domain, this is just an RC circuit with a rise time. So as current flows into the resistor, this capacitor will slowly load up, and it will have a rise time. So that's almost like a step response. It is actually a step response, and I wanted you to have a specific rise time. So in this case, the cutoff frequency is 2.38. I can calculate what my frequency response is. I can also simulate it by looking at an AC analysis of the circuit if you want, but I think most of you will be familiar with RC circuits. And then I can also calculate the rise time of R and C here, and ensuring that I have a rise time that still gives me 100 or within 100 milliseconds, it gives me 90% of the full step response. So the circuit that the signal that comes in here has an AC component and the temperature, the AC component being the noise of 50 hertz. It also has a temperature. The temperature could have a change, which will be very low frequency, and then the signal here will be filtered. So let's have a quick look at what this looks like. I'm just going to simulate it. Right, so now that it's simulated, let's just recap quickly. I gave it an instruction to jump 1 degree, jump back 1 degree, and then jump the full range to the maximum degrees. So from 34 to 42, 8 degree jump there. So if you consider this output, at the bottom is the input, top is the output, you can see that there's a wavy signal coming in here. It has a response, so it's steps. So if you look at 100 milliseconds, and over here, it should have reached that point already. Goes down slowly, goes up, jump here. So let's consider how this is looking good, and you can see it goes from in the order of 600 millivolts. It jumps up to the order of 4.15 volts. So many of you wanted to know what we wanted to see with the noise. So I'm just going to zoom in here. And you can see that if I measure the noise, it goes from a level of 620 more or less. It goes down to a level of, what's that? 653. So that's a difference of 47, but I told you the deviation must be less than 50, so it's basically half of that. So in this circuit, I'm meeting that requirement. So I am suppressing the noise from a 1 degree deviation, so an amplitude of 1 degree, to an amplitude of more or less 25 millivolts. So I'm meeting that requirement. So that's all good. So now the question is, do I actually meet the step response? So now I want to check what the step response is. So in order to do that, I need to increment the temperature here. So let's just do that. Oopsie. And let's just do that. So I'm just going to let it run. And you will see that I've taken away the noise here. The noise is now 0 because I don't want to simulate the noise. I want to see what the step response of my circuit is. So I'm just going to compile it again, and now it should compile a bit quicker. Right, so it's finally finished, and now I can just generate the stimulus again. So here's my stimulus signal, adding a plot plane, and over here I'm just going to plot V out. There we go. So let's have a look at whether this then meets the requirements. So as you can see, this has settled, and it has settled at, let's have a neat look deep inside. So its final resting place you can actually calculate if you want, but if I were to measure it, just going to bring in my cursor. If I measure it, I can see that it's stepped from here. It has stepped to the final resting place is 1.05 volts. So you can go and calculate what you expected if you consider your gain and you expect 1 degree change. So I have 1 degree is 10 millivolts times 45, and that is, well, 47 was my gain, sorry. So it's more or less 470 millivolts that I'm expecting the jump to be, and I'm getting 440. So that's what I'm getting. I'm obviously not a perfect circuit. I'm getting 440, but you can see that it's settled there. So all I want to check is that it has reached 10% of the final value within 100 milliseconds. If I go back, has it reached 90% of that? And the answer is, if I consider that the final value is 440, what seems to be 442, let's make it 450. For argument's sake, you can obviously go and calculate or measure the total one after a few hundred milliseconds. It has reached 360. So that is not 90%. So that means that my filter is filtering too low. So this 2.5 or 2, whatever, 3 kilohertz that I have is too low. So I'm fiddling around with it. You're obviously supposed to go and calculate this perfect middle point, but that is too low. So if I just rerun this, then you will see that the response time will be quicker. I'm just actually going to zoom out here so you can see what I mean. So again, the filtering was fine. I suppressed the noise, but the issue is that my response time was not good enough. So now I've changed this capacitor here, or at least this resistor here. And if I go back to it now, what you can see is that the change is 450 millivolts, and if I measure at 100 milliseconds after that change, it's now 400 millivolts. So by changing that capacitor, so what I've done is I've improved the step response, but the issue is that that would have worsened the noise. So the noise will now be a bit higher. So you needed to find that perfect middle ground between finding the adequate step response and then filtering that enough. So obviously an RC filter seems to be able to do it. If it wasn't, then you had to use whatever other filter you had at your disposal. Over here, I'm just showing the total response. So I'm just showing that my full output goes up to 4.3 volts. And at the bottom level of that range, it goes down to, at the moment, 612. Right, so that seems to be working. Right, so if I add back the noise, then you should see that the noise is still within the limits of the specifications. So as you can see now, I still have this noise on the input. I'm just going to blow this up slightly. There's this big 1 degree amplitude sinusoid on top of my signal. And if I zoom now, I should see, despite the fact that I'm still meeting my I'm meeting the rise time requirement, you should see that I'm still meeting the objective of limiting the noise or suppressing the noise. Just get my cursors back here. So it goes from a low of 602 up to a high of 658. So that's peak to peak. Half of that will be just over 28 millivolts. So I'm still meeting the objective of suppressing the 1 degree noise to 18 millivolts. So that's more or less the idea. It's a very nice compartmentalized design, so you don't have to worry about the different aspects of it. And this is really something that I take from coding. It's a good idea to try to divide and conquer the problem. Try to split it up into small parts, and then consider the tools that you have at your disposal, and then work with that.